In this video, we're going to take what we did for double integrals and using Jacobians to transform them into something simpler. We're going to apply that process to a triple integral. And as you might expect, it's just going to be a slightly longer process, more variables to handle. So we're going to do three things. We're going to state what the Jacobian is in 3 dimensions. We're going to state the theorem that tells us how to put it all together, but it's going to look a lot like the theorem for a double integral. And then we'll do an example, right? So let's start with the definition of the Jacobian in 3 dimensions. So first, what we need to do is, so the idea is we're going to be converting one solid that's expressed in terms of x, y, z, our standard rectangular coordinates. And then we're going to transform them with a clever choice into another 3-dimensional space, but we're going to use the variables u, v, and w. So let's write down what that transformation would look like. So here's t. So let's say our x variable will be a function of u, v, and w. Then our y variable will be another function. So I can't use g, I'm going to use a different letter. It's going to be quite the alphabet soup here. And then z will be another function. All of these expressed in terms of u, v, and w, right? So x, y, z are like our existing 3-dimensional variables, and now we're expressing them in terms of these new 3-dimensional variables, u, v, and w. So I'm not going to state all the, I'm not going to write all the assumptions, but I'll tell you what the assumptions are. So these three functions, g, h, and p, they're all differentiable on some region in the u, v, w space. So their partial derivatives exist. And then here's the Jacobian. So this would be I guess you would say the simpler way to write down the Jacobian. So u, v, w in that order. Or you could use that kind of partial notation where you have the old variables kind of in the top, and then the new variables in the bottom, u, v, w. So either one we can use to denote our Jacobian. But what it's going to be now, it's going to be a 3x3 determinant. So let me set it up what the determinant will look like. So in the first row, you're going to have the partial derivative of x with respect to u, x with respect to v, and x with respect to w. And then we're going to repeat that process for y and z. So the second row is the partial derivative of y with respect to u, y with respect to v, and y with respect to w. And then finally, the third row, the partial derivative of z with respect to w, z with, not w, z with respect to u goes first. So we have to keep that order, right, that standard order. So u, v, and then the partial derivative of z with respect to w. Right, so again, you can see in the 2x2 case, we had or I should say the 2-dimensional case, we had a 2x2 determinant. Now in the 3-dimensional case, we have a 3-dimensional determinant. So that adds to again, the workload. All right, so once you have this, then now the question is, how do we put this all together, right? So what do we do in terms of applying using this Jacobian to perform the transformation? Now, as I did for double integrals, I didn't write, because it's a pretty long theorem, and I've even already summarized it, but I have it, I'm just going to paste the theorem, and then we're going to walk through the kind of key pieces. But when you look at it, if you look closely at what we did in the 2D case, you'll see something very similar here. So let me go ahead and paste this, and there's our theorem, right? So this is the theorem that tells us how to utilize this transformation in 3D, right? So there are our equations, and it's just saying some things about the transformation. Again, it's going to convert solids or regions in x, y, z to solids and regions in, why that's blinking. Come on. And then, right, so it's going to make the transformation between the two spaces. And again, we need the transformation to be one-to-one. That's a technical piece. We need the function that we're integrating to be continuous. But basically what we're going to do is we're going to replace all the x's with the g function. We're going to replace all the y's with the h function, all the z's with the p function. So again, we're switching our function over in terms of u, v, and w. And then here's the key piece right here. That same thing that we had to do in the double integral also shows up in the triple integral, where it's the absolute value of the Jacobian, all right? And then notice the integral, the triple integral on the left is in terms of x, y, z, and then the triple integral on the right is in terms of u, v, and w, right? So that's the, when you look at the theorem, pretty similar, but yeah, there's a lot going on, all right? So here's our, we're going to do an example, and it will take a little bit of time, right? As we can expect, the triple integrals will be longer. So let's take our example, and let's write down the triple integral that we're given in terms of x, y, and z. So the function, so there's our triple integral over some solid, and I'm going to keep the function pretty simple. It's just going to be x times z dv. And then let's state where the solid is. So the solid is going to be one of those, you know, we love saying this word, parallelepiped. So S, which is just kind of like a skewed box, so is the parallelepiped. Bounded by, and we know for these kind of boxes, we need lots of planes to box them, right? It's like, how many faces does a rectangular box have, right? That's how many planes we need. 6, right? So let me kind of write them up. So one plane is y equals x, the other plane is y equals x plus 2. And we can tell that these are going to be, you know, parallel just by looking at the, now remember, this is in 3 dimensions, and that's why these are planes, right? But you can tell that those two are going to be parallel. And then here are the other, another pair, so z equals x, or z equals x plus 3, again, parallel planes. And then this is probably the most recognizable one. Z equals 0 is just the xy plane. And then z equals 4, it's just 4 units above that. So again, this, you know, the z equals 0 would be like your floor, and then the z equals 4 would be your ceiling. Again, parallel, right? And we could sketch this, but like precisely, but I'm just going to give you, without drawing the x, y, z axes, let me just give you a sketch of what it might look like in a somewhat standard orientation. It's basically, you know, that will be one face, and I know this doesn't look parallel. And then if I kind of copy and paste this like that, and then let me connect these right here, and then connect these right here, and then this one back here, right? That's kind of what it looks like, but it would be, you know, in the standard coordinate axes orientation, right, or left-hand orientation, it would be somewhat skewed. It wouldn't be the standard rectangular box, right? So the triple integral, believe it or not, would be a little difficult to set up if we keep it in terms of x and y. All right. So first we have to choose the equations for our transformation, and here's what we're going to do. Very similar to what we did in the double integral case. I'm going to take each pair of these equations, and I'm just going to rewrite it in this way, where I'm going to have all the variables on one side of the equation, and then hopefully just have constants on the other side, because those constants will actually help us quite a bit in the transformation. So if I take the first pair and I write y minus x equals 0 and y minus x equals 2, and that's good. And if I take the middle pair, I would have z minus x equals 0 and z minus x equals 3. Now, I don't have to do anything for the third pair because I already have the variables. In fact, there's only one variable in this pair of equations, but it's already kind of isolated on one side, and I already have constants on the other side. So here's what I'm going to do. I am going to choose this expression as my u, and then this expression as my v, and then I'm just going to make a straight old swap and say that the z is equal to w. So let's write that down. Right, so let's write this down. So we're going to let u be equal to y minus x, v be equal to z minus x, and w be equal to z. And what that gives me now, it gives me the limits in terms of u, v, and w, but as constants. So this one tells me that u is between 0 and 2. This one tells me that v is between 0 and 3. And this one tells me that w is between 0 and 4. So like this. So let's take a look at what this would look like if we were to sketch this in the u, v, w space, right? So this one I'm actually going to sketch, and let's say this is my u axis. This is my, let's say this is my v axis, and let's say this is my w axis. So I need 1, 2, 3, I'll just do 4 on each. 1, 2, 3, 4. 1, 2, 3, 4. So in terms of this solid now, it's 0 to 2 in the u, 0 to 3 on the v, and then 0 to 4 on the w. So it looks like this. Now this would be a standard, like that, and then that, and then that, and that one, and then yeah, just connect those things. Not great, but you can see it's better, right? What it does, this transformation is a simple transformation, but it kind of straightens out this smooth, or not smooth, this skewed box to where the angle at the corners, the angles are now 90 degrees as opposed to some other angle like right here, right? So not a really complicated transformation, but geometrically it really helps us out, because now when we set up our triple integral, we're going to have basically a rectangular solid that we're integrating over. All right, okay, so we have our limits. Now let's work on the Jacobian. The Jacobian is going to be the big part, because the thing about the Jacobian is we need to express x, y, and z in terms of u, v, and w. So I basically need to solve these equations to write it in the form x equals, y equals, and z equals. Well, we already have that. So let's start from the bottom equation and work backwards. So we know that w is equal to z. That means I'm going to state the obvious here. Z is equal to w. And then what I can do is kind of use a substitution and then plug this into the second equation and replace z and with w. So if I do that, so the second equation looks like this: v equals w minus x. And if I solve this for x, let me write it over here, I'll get that x is equal to w minus v. So w minus v, just doing a little bit of algebra there. And then lastly now, I need to write y in terms of u, v, and w. So now that I know x, I'm going to go to the top equation, the first equation, and solve for y. So let's do that. So let's write it down. So u equals y minus x. So therefore, if I solve this for y, I'll get that y is equal to u plus x. So u plus, but I know what x is. It's v minus w. So just plug that in. So I'll have w minus v. So that will be our u equation, right? So these are the three equations that we need, and now to set up the Jacobian, we need all these partial derivatives. So our Jacobian, I'll just use this notation. Now, because the equations are all linear equations, then it means our partial derivatives are going to be nice constants. So let's start with the x equation and find the partial derivative in terms of u, v, and w. So because there's no u in my x equation, then the partial derivative of x with respect to u is 0. The partial derivative of x with respect to w is 1. Or actually, we need first v. The partial derivative of x with respect to v is -1. And then the partial derivative of x with respect to w is 1. Right? Now let's turn to the y equation. The partial derivative of y with respect to u is 1. Y with respect to v is again -1. And similarly, the partial derivative of y with respect to w is 1. And then finally, looking at the z equation, the partial derivative of z with respect to u, there's no u in this equation right here, so that gives us 0. There is no v in that equation either, so the partial derivative of z with respect to v is 0, and then the partial derivative of z with respect to w is 1. All right, so there is our 3x3 determinant. Thankfully, it's not too complicated at all. And let's do our first row expansion. So it's going to be 0 times, and then block out the first column in the first row, and we're left with this little 2x2 determinant like this. And then the middle term is going to be minus, and then we have -1. Take this term and then block out the middle column and the first row, and we're left with 1, 1, 0, 1. And then last term is +1 times, block out the first row, third column, you'll have 1, -1, 0, 0. All right, so then let's use our 2x2 determinant formula. Now the first term is going to be 0 because we're multiplying that one by 0, so I don't even need to calculate this. I just know that that's going to be 0. The next term is going to be a +1 times, and then we do 1 times 1, -1 times 0. And then the third term, actually that one's going to work out to be 0 as well, because it's going to be 1 times 0 minus -1 times 0. So we have this. So all that, and we get a Jacobian of 1. All right. Okay, so we have our Jacobian, we have our x, y, z equations, we have our limits, time to evaluate. All right. So let me write down the original integral. It's over our original like skewed box. And remember, the function is x times z dv. So now let me write down the iterated triple integral. And I'm going to choose to integrate. The order doesn't matter. Again, Fubini applies. I can do it in any order I want. I'm just going to do, let's do du, dv, dw. So let's write down our triple integral there. And then the limits for u, we have them right there. There's our inequality, 0 to 2. The limits for v, 0 to 3. The limits for w, 0 to 4. And then now what I need to do is plug in the x equation for the variable x. Now remember, x is w minus v, so I'm going to put that there. And then the z equation is just w, so we have that. Right, so it looks like that. And then we're supposed to multiply by the absolute value of the determinant, so I'm going to put that in there just for completeness, but that's our integral. Now it's a triple integral, but unfortunately there's no way for me to factor this completely to where one factor only has w and the other one only has v. So I won't be able to use that nice little factoring trick in our triple integral. So we really just have to integrate one integral at a time. And let's start with the inner integral. So we're going to go from 0 to 2. Let me distribute the w. So I'll have w squared minus vw. Hey, I drive a VW. So we got du there. Now the nice thing is none of these terms have a u. So this whole thing is treated as a constant. So you can write it as that constant, which is w squared minus vw times u, and then you evaluate it at 0 and at 2. And remember, we're plugging in for u here. So we will have 2 times this quantity minus this quantity times 0. So it just ends up looking like this if I distribute in fact, let me write it down like this so you can see what we're doing. So we got minus vw, and then it will be times 2 minus 0. And then if I distribute the 2, I'll have 2w squared minus 2vw. All right. Next up, we're going to do the middle integral, which is the way I have it set up in terms of v. So that goes from 0 to 3. And we have 2w squared minus 2vw and dv. Now, if you wanted to, you could factor out this 2, but that's about it. We can't factor anything else out. So if you take out the 2, and then let's write down the antiderivative of w squared with respect to v, but we're treating w as a constant now for this integral. So it's going to be w squared times v. And then now I have to integrate vw with respect to v. So the w here is a constant multiple, which will be brought down, and then we'll have 1/2 v squared times w, and then that goes from 0 to 3. Now, it was probably a better idea to leave the 2 in, so let me kind of distribute that, and then we'll evaluate. So we'll have 2w squared v minus v squared w from 0 to 3. And remember, we're plugging in for v now, right? So let's see what that looks like. So at the upper limit, plug in 3 here. We'll have 2 times 3, that's 6, so that's 6w squared. And then here, 3 squared is 9, so minus 9w. And then at the lower limit, everything is 0, right? So everything is 0, so minus 0. So there we go. So our second integral is now done, and we have one more integral to go. All right. And yeah, let's so what is that one? That one's with respect to w, and then we're going from 0 to 4. So we have 6w squared minus 9w dw. So power rule on this one gives me 2w cubed. Power rule on this one gives me minus 9w squared, or we could say 9/2 w squared, and then that's from 0 to 4. So what do we have here? So it's 2 times, so 4 to the 3rd power is 64, minus 9 over 2, 4 squared is 16, and then, so that's at the upper limit. Again, at the lower limit, everything is 0, and then that evaluates down to a nice 56. All right. So I told you it was going to be a long process, but it's just more of the same, right? One extra variable, one extra equation in the transformation, one higher determinant, and one extra integral when we actually do the conversion, right? So needless to say, I would say that this example that I've chosen is a pretty standard one if you're going to get something like this, let's say on an exam. Because otherwise the process just gets it's not fitting for a timed exam just because of how much stuff goes into it, right? But it's just extending what we did in the double integral case. So hopefully you found that useful, possibly even interesting, maybe even fun. And let's see what the next set of videos hold for us. See you soon.